So now we did KW, right? I told you about we started KW somewhere over here. Yes. So I'm just going to recap everything shortly. You had this equation where water was ionizing, right? And it was forming H plus 1 and OH ions, right? And I told you that this was the actual equation. H plus 1 is H3O plus 1. Anyways, we went with the equation and I told you about the ionic product of water, which is Kc of water. You don't write water in the expression. Why? Because it is in excess and its concentration would almost be constant. It's not going to change. So the actual Kw, or the equilibrium constant for the ionization of water, is this thing, which always has a value of 1 times 10 power minus 14, because the amount of ions that you have, so the amount of ions that you have in solution, that's 1 times 10 power minus 7 at room temperature. But any equilibrium constant, it changes with temperature. So if you have a higher temperature, the equilibrium constant is going to increase, and it's going to ionize more. Now, the importance of Kw was, we talked about the importance of Kw. I told you that everything is happening in water on planet Earth. So either the concentration of H plus 1 and OH ions is the same, or we studied that if you add an acid, the concentration of H plus 1, it increases, and the concentration of OH ions, it decreases. And the next one was the opposite, that you could add a base, and the base would increase the concentration of OH ions, and it would decrease the concentration of H plus 1 ions. So the water usually determines the environment. That's whenever two things are reacting, it's usually surrounded by water. So there are different types of environments: neutral, acidic, and basic environments. And every reaction they're very sensitive to pH. So we talked about that. I talked about tracking the concentration of H plus 1. I told you that it's very difficult to make graphs when values are too small or too big. So instead of tracking the concentration of H plus 1 ions or OH ions, what you do is you track the log of those values, which is that those values are expressed in the powers of 10. It's easier to make graphs for that. And I talked about Kw. I took the log on both sides. And when we take log, our Kw expression becomes this. This is the log of Kw, which is 1 times 10 power minus 14. And H plus 1 concentration and OH ion concentrations were being multiplied. So when you take log, the multiplication changes into addition. So, and because I was multiplying everything with a negative sign, the addition becomes subtraction. So it's 14. This thing is called pH, and this thing is called pOH. Okay, is this clear? This is all what we did yesterday. Ruba and Abdullah, Lubena, is this clear?
Yes.
Okay, can you hear me properly?
Sir, just one question.
Yes.
If there's a minus sign over here, it can also be a positive?
Any, which one? This one?
In P, sir.
P is always defined as the negative of log. I mean, you take log and it's being multiplied by minus 1. It can't be positive. I mean, it's defined as minus, right? And I did explain to you why you were taking minus values, because if you take log of concentrations are usually in decimals. So this is 10 power minus 1, this is 10 power minus 5, this is 10 power minus 2, right? So if you take just the log, we get powers like minus 1, minus 5, minus 2. So if you're trying to track it, instead of tracking negative values, it's much better to actually track positive values. It's much easier to make a graph of positive values instead of choosing the negative scale. So that's why they multiply everything by minus 1. Ruba, is this clear? Is this thing clear? Sorry. Ruba, were you able to hear what I was saying?
Yes, sir. I understood.
ठीक है. So the negative sign is just there so that you don't get values in negative. That's why they multiplied it by negative. Uh, Now we're going to do questions. Remember, it's always going to be the concentration of H plus 1 ions. Now, what the negative, what effect when you multiply things by negative, what happens? Uh, there is one problem that happens when you multiply something by -1, and that happens to everything. It always happens. I mean, this is what we did over here. Instead of taking just the log, we took the negative log. We basically ended up multiplying everything by -1. When you multiply things by -1, the smaller value, for example, you have two numbers, you have 3 and 5, right? So which one is the bigger number? That's obviously 5. But if I multiply both sides by -1, this would become -3, and this would become -5. Now, which one is the bigger value? The smaller value actually turns into a bigger value. Is this point clear that that there's this thing that happens when you multiply things by -1, and that is that the bigger value actually becomes the smaller value, and the smaller value actually becomes the bigger value. Is this point clear?
Yes, sir.
Yes, sir.
So smaller becomes bigger and bigger becomes, and vice versa. Now, because of that, your pH scale is upside down. Because of that, you have pH being low. As because of that, if you have pH that's low, that means the concentration of H plus 1 is high. I mean, that's why your pH scale is kind of the opposite. If the pH is low, the concentration of H plus 1 is high because you've multiplied uh, everything when you were taking log everything by -1. So multiplying something by -1, it kind of turns the scale upside down. And similarly, if the pH is high, like if the pH is 13, that means the concentration of H plus 1 ions is going to be very low. So is this point clear? That's the effect of multiplying by -1 has on the values. Is this clear?
Yes, sir.
Yes.
Yes.
So now the next thing we're going to do is we're going to start calculating pH, right? And we're going to talk about strong acids. I mean, I know calculating pH of strong acids as well as strong bases. So strong acids and strong bases. Now, calculating their pH is kind of very easy. You just have to figure out the concentration of H plus 1 ions, and you just have to take the negative log of that. And the reason that's easy is strong acids, they fully ionize. They fully ionize. What that means is that let's say I have HCl, and I have HCl, it's 0.25 mole per decimeter cube. Now I know that this HCl is going to fully ionize. It's going to ionize, and it's going to produce H plus 1 ions, and it's going to produce Cl minus 1 ions. Every single HCl molecule would ionize. So if the concentration of HCl is 0.25 mole per dm cube, the concentration of your H plus 1 ions is going to be exactly the same. It's going to be 0.25 mole per decimeter cube as well. Hence, there is no confusion. You can simply calculate pH. What is pH? pH is negative log of the concentration of H plus 1 ions, which in this case would be 0.25. And tell me what the value is. My desktop calculator probably wouldn't. Negative.
0.6.
Okay, so it's 0.6. I mean, up to, let's say, two significant figure. What's
0.60.
so you're getting 0.60. That's your pH. So it's kind of easy. It's not that difficult calculating pH of strong acids. So you can simply directly calculate any pH. There's no issue with that. What about strong bases? Now, for example, I have NaOH, and the concentration of NaOH is 0.010 mole per dm cube. That's the concentration of NaOH. It says it's a very strong base. It's going to ionize fully. It's going to produce two ions. One is Na+1, the other one is OH-1. Now, when it comes to pH, remember we talked about this thing. Second. I said, remember we talked about this thing, that I told you that we are always tracking H+1 concentration. No one really cares about OH concentrations. Why? Because they kind of understood, like, if the reason we're only interested in H+1 concentration is because the OH concentration would be exactly the opposite. So if H+1 concentration is high, then it's kind of implied that the OH concentration is low. So you don't have to actually go and calculate the OH concentration. Vice versa, if the H+1 concentration is low, it's kind of implied that the OH concentration is going to be very high. So, which is why we only track H+1. I mean, we don't increase our workload. We don't really care about OHNs because by just tracking H+1, you'd be able to figure out OHN automatically. Now the thing is, कि यहाँ पे ना there is what about bases? Now the problem with bases is, like, even if you look at the equation, the only thing you can actually find out, I mean, there is no H+1. What you can only figure out is the concentration of OH ions, right? So the problem is, the only thing that you could do is you could calculate pOH. I mean, because you don't have a choice. You know that pOH is the negative log of the concentration of OH ions, right? Although, if you make an effort, you would be able to actually calculate the concentration of H+1 ions by using the KW expression. Because the KW expression, you can either do that. I mean, that's going to be slightly time consuming. You know that KW is H+1 concentration into the OH concentration. What you could do is, you already have the OH concentration. This is 0.10 mole per dm cube. So OH ions would be exactly the same.
Sir, you minus it by the 14, right?
That's what we're going to do. But if somebody is going to ask you about H+1, I mean, you can use this expression, like, you know that KW is H plus, I mean, you know the value of KW, it's 1 times 10 power minus 14. You can plug in the value of OH ions and you can get the concentration of H+1 ions. So that's one way of doing that. Or you can just keep things in log. You can find pOH. What is pOH over here? It's minus log of
2.
That's a 0.010. So that's coming out to be exactly, it's 10 power minus 2. So it's obviously coming out to be 2. And you know that the inequality, the identity is that pH plus pOH is equal to 14. So you don't know what pH is, but you know what pOH is. So it's going to be 14 minus 2, and that's going to give you 12. So the pH is coming out to be, 12. Is this clear?
Yeah.
Yes.
So strong acids, strong bases, and you should be able to figure out the opposite, the reverse. Let's say the pH is given. pH of HCl is given, and they're saying that the pH is 1.5, and they're asking you what is the concentration of HCl.
12.5.
How would you find that? It's, you know that pH is 1.5, right? What is pH? pH is the negative. I mean, now you have to do the reverse. pH is the negative of the log of the concentration of H plus 1 ions. And that value is 1.5. The first thing is you're going to take this negative sign over here and take it to the other side. So the negative sign goes to the other side, and then you take the anti-log of both sides. So what is the anti-log? Remember, anti-log is 10 power x. ठीक है, remember inverse log or anti-log is 10 to the power x. So you're going to take the anti-log of this side. So h plus 1, there's only going to be h plus 1. The log gets cancelled out. And you're going to take the anti-log of this, which is going to be 10 power minus. It's going to become 10 power x, which is 10 power minus 1.5. Is this clear? And what do we get? What is 10 to the power?
31.6.
How much?
No, 0.0316.
This is 0. So that's coming out to be 0.0316 mole per decimeter cube. Now we found the H plus 1 concentration, so finding out the HCl concentration would not be that difficult because it's a strong acid. And both of them are going to have the same concentration. It's going to be 0.0316 mole per dm cube. So the concentration of HCl would be exactly the same.
Okay.
So just remember how to take the opposite, do the opposite. Like if pH is given as 1.5, the concentration of H plus 1 would be 10 per minus 1.5. That's it. If pH is given as 5, the H plus 1 concentration would be 10 per minus 5. So just remember, how do you calculate the opposite now? And similarly for bases, if the pH of NaOH is given as so the pH of NaOH is given as 13, and they're asking you to find the concentration of NaOH. Now, the first thing is you're not going to deal with pH. You're going to convert pH into pOH. You know that pH and pOH is equal to 14. pH is given as 13. So that means your pOH comes out to be 1, right? And you take the inverse. The inverse would be OH ion concentration would be 10 power x or 10 to power minus 1, which is basically 0.1 mole per dm cube. Okay, is this clear?
Yes, sir.
So that's coming out to be 0.1 mole per decimeter cube. And so this is coming out to be 0.1 mole per decimeter cube. So remember, bases convert everything into pOH. Much easier to do that. Bases are usually not in your, I mean, you'll be asked about this, but otherwise bases are not really part of your course. Anything that we study from now on, I mean, they're going to ask you about of strong bases, about pH of strong bases, but nothing after that. So this is all about pH and pOH. Now I'm going to start talking about strong acid and strong bases is kind of easy. What I'm going to start talking about is, just a second. So what I'm going to start talking about is weak acids. The first thing is which acids are considered to be weak acids? What do you know? Which acids are weak acids? Anyone, any idea? Like you have studied this a lot.
That don't dissociate fully. Ionize.
See, they don't. First thing is they don't ionize fully. Most organic acids are weak acids. And they ionize partially. So they don't really produce a lot of H plus ions. So they produce fewer or lesser H positive ions. Now the biggest issue over here is when you have a weak acid, for example, all organic acids are weak acid. You've got ethanoic acid, right? So ethanoic acid doesn't really like to ionize. So if you have 0.15 mole per dm cube of ethanoic acid, the problem that's going to happen is that the amount of ethanoate ions that are going to be produced, or the amount of H plus 1 ions, that's not going to be 0.15 mole per dm cube. That's going to be a lot less than 0.15 mole per dm cube. Because it's not going to ionize, it's not going to produce H plus 1 ions. Okay, is this clear?
Yes.
Yes.
So that wouldn't be really ionizing a lot. So now we have an issue. Like if you don't know what's the concentration of H plus 1 ions, we wouldn't be able to calculate pH. But it's an equilibrium reaction. So equilibrium reactions, whenever you have any equilibrium reactions, there's going to be a ratio. There's going to be a certain quantity of products that would be formed, and there's going to be a certain quantity of reactants that you'll have. So that is known as Kc. Kc is the concentration of the products divided by the concentration of the reactants. Now this value of Kc is a constant unless you change temperature. So maybe there would be a lot of products formed and a lot less reactant, so the ratio is going to be high. Or maybe it's going to be the other way around. The reactant concentration would be very high and the product concentration would be very low. So depending on this ratio, you will be able to figure out how much ethanoic acid ionizes. Is this clear?
Yes.
Okay. So
Yes, sir.
depending on this ratio, I mean, there's going to be an equilibrium constant. And that equilibrium constant is going to give us an idea that what's the ratio between the concentration of the products and the concentration of the reactants. Depending on that ratio, we'll be able to figure out whether it's a strong acid or a weak acid. So all acids are going to ionize in the same way, all weak acids. For example, I can take any acid. I have butanoic acid. So this butanoic acid is going to ionize in exactly the same way. An acid is anything that's capable of producing H plus 1 ions when it breaks down or ionizes. So I've got NH4 plus 1. It's going to turn into NH3 and H plus 1. Now, one thing you'll notice is that all acids dissociate in kind of the same way. It's always there's an acid and it breaks down to produce a random ion plus H plus 1. So we can have a general equation for acids, and that general equation can look something like this, that it would be HX, and that acid would ionize and it would produce X minus 1 ions and it would produce H positive ion. That's going to be our general equation for the dissociation of an of an acid. Okay, is this clear? That all acids, they have an H plus
Yes.
1 ion. Actually, all acids, they have an H plus 1 ion attached to something. Okay, whether it's CH3CO minus 1 ion, or whether that H plus 1 is attached to C3H7CO minus 1 ion. Whatever it is, I don't really care what X is. Okay, we just don't care about X. The only thing is an acid is made up of an H plus 1 ion attached to something, which we don't care about. It's going to break down, it's going to produce H plus 1 and whatever's left. So all acids dissociate in pretty much the same way. And now, do you all agree with this statement? All acids dissociate in the same way. Sorry, Lubena, is this fine? Abdullah?
Sir, but weak acid don't dissociate much, so they don't.
No, so there's a reversible reaction. I mean, the amount of ions that are going to be produced, they're going to be a lot lesser compared to this. Like if you have 1,000 molecules, the amount of ions that are going to be produced are going to be very, very less compared to this. Is that clear?
Okay.
Now the problem. So I'm just going to point out one problem with this, and that is, I said that this could be used as a general equation for dissociation of all acids. That any acid, it produces an H plus 1 and there's something left, right? So what about diprotic and dibasic acid? So what happens if you have a diprotic, which means that it has 2 protons? Or a triprotic acid, also known as tribasic acid. What happens in that case? So for example, you've got H2SO4. It would ionize. It would produce an SO4 minus 2 ion, but it's going to produce 2 H plus 1 ions, right? So this general equation is kind of different from this one. The only thing different is that there should have been 2 H plus 1 over here, right? So the problem is that this general equation that I'm coming up with, it doesn't really fully agree with this equation. I mean, this acid is dissociating slightly in a different way. Same goes for phosphoric acid. Like if you have H3PO4, that's capable of producing a PO4 minus 3 ions, and it would release 3 H plus 1 ions. Is that clear?
Yes, sir.
Okay. But the thing is, Ruba, is this clear? Shafak, Lubena?
Yes, sir.
Okay. So do you get my point that diprotic and triprotic acids, their equations would be slightly different compared to the general equation I've stated over here. So the thing is that whenever you're dealing with diprotic or triprotic acids, remember this, they also release 1 H plus 1. Like you have SO4 minus 2, right? SO4 minus 2 is H2SO4, sorry. So this is your H2SO4 molecule. Now, what happens is this H2SO4 molecule, it doesn't release the 2 H plus 1 ions at the same time. What happens is it first releases one of the H plus 1 ions. So there's an H2SO4 molecule. It dissociates, ionizes, and it ends up producing HSO4 minus 1 ion and releases only one of the H plus 1 ions. So the first thing is one of the H plus 1 ion, it breaks off and leaves. And once that happens, once that is gone, so this ion has left, leaving behind a negative charge. The H plus 1 over here has broken off. In the next step, you have this HSO4 minus 1 ion, which is this one. So in the next step, there's going to be HSO4 minus 1 ion. And in that HSO4 minus 1 ion, another of the H plus 1 is going to break away and leave, leaving behind SO4 minus 2 and another H plus 1 is released. So what I'm suggesting is that even if you have a diprotic acid, the dissociation doesn't happen in one go. It happens in two steps. There's going to be one step and then there's going to be another step. So your general equation for acid dissociation, which is this one, kind of fits with both of the steps. I mean, this one exactly matches. I can just copy paste this. So this one kind of exactly matches each one of the steps. So the general equation kind of fits exactly with this. It wasn't fitting with the overall equation, but it was fitting with, I mean, this general equation fits with each of our steps. That's step one. So our equation looks exactly like this, like step one. And our second step, the second dissociation, it also looks exactly the same. So is this point clear that this general equation also works with dibasic acids?
Yes.
Yes, sir.
Yes.
And about dibasic acids or tribasic acids like phosphoric acid, what's going to happen is don't think of them as one acid. Think of them as two completely separate acids. I mean, the first step, it's this molecule that's releasing an H plus 9. In the second step, the species that's acting as the acid is a separate species. It's a different species, right? Like in the first step, so think of a dibasic acid or diprotic acid as two separate acids. In the first step, it's H2SO4 that's ionizing. In the second step, it's HSO4 minus 1 that's ionizing. Which one do you think would be the stronger of the two acids? I mean, which one would it be easier to lose H plus 1 ions?
HSO4.
Which one? This one?
Yes.
Is it going to be a stronger acid or a weaker acid?
Stronger.
Remember, it has a charge of negative, right? So would it attract H plus 1 or would it lose H plus 1 if it has a negative charge? For something that's negatively charged,
Will attract, yeah.
it would be harder to actually lose H plus 1 ions, right? I mean, instead, it would be attracting H plus 1 ions. So this is going to be a weaker acid. This is going to be weaker. The first dissociation is going to be stronger. So when you have a dibasic acid, think of it as two completely different acids. The first step, this dissociates, ionizes, produces H plus 1 ions. In the second step, the HSO4 minus 1 is the one that's losing an H plus 1. So this is going to behave as it will have different properties as an acid. This one will have this one is going to behave as a stronger acid, whereas this one would behave as a very weak acid. Is this clear?
Yes.
Yes, sir.
ठीक है. Islam. And pretty much the same thing goes for phosphoric acid, which is like H3PO4. Don't think of it as one acid. It's not going to release the H plus 1 immediately. Everything would happen in steps. It's going to form HPO4 minus 2, H2PO4 minus 1 ion, and release an H plus 1 ion. In the next step, the H2PO4 minus 1 would release another H plus 1 ion, so it's going to form HPO4 minus 2. And in the last step, the HPO4 on it. So last step, it's going to be HPO4 फिर हो गया एक सेकेंड it's going to be HPO4 minus 2 and that would be releasing NH plus 1 ion. So the three H plus 1s would not be released simultaneously. And every time a different thing would be releasing an H plus 1. This would be acting as an acid. In the next step, it's going to be this one that's acting as an acid. So which one out of the three would be the weakest acid?
The PO4 minus 2.
Okay, so the acid strength, it would decrease because minus 2 would instead be attracting H plus 1. It would be very hard for it to actually lose an H plus 1. So this one is the one that's going to be the weakest. The first one is going to be it will have the strongest dissociation. So think of each dissociation as a separate, completely separate, independent dissociation. Hence, your general acid equation would still work, even if it's a tri-basic, because you're not going to take the three H plus 1 ions together. So, is this clear? कोई question नहीं है?
Yes. Yes.
चलें, let's just remember this is the general equation. ठीक है, we're going to work with this next time. Okay, everyone. Take care, Allah Hafiz.